Hello there. Today we are talking about the standard error of the difference. Now, the standard error of the difference is represented in this way. So, you'll see that the first set of symbols to represent it are the symbols that we use for the standard error of the mean, but with subscript 1. Then we're subtracting. We have a minus sign with x bar subscript 2. This is how we remember. This is the set of symbols we use to represent the standard error of the difference. This first one is more important because it is how you can remember what this is and how it's used. If you remember the standard error of the mean, you might remember that it was used in calculating a z-score for a group. Which had the formula x bar minus mu over the standard error of the mean. This gets substituted in when we're calculating a z-score for two groups instead of just one group, because here we have x bar minus the population mean, so the sample mean minus the population mean divided by the standard error of the mean. Here we have a z for two groups, which is equal to x bar 1 minus x bar 2, and all of that minus mu 1 minus mu 2. That is over our standard error of the difference. So, if that's how we use it, how are we going to calculate the standard error of the difference? Well, let's head back to green, and I will show you. So, we're taking the variance of our first population and dividing it by that population's n. Then we're going to add the variance of our second population, which is divided by that population's n. And we are going to take the square root of that entire thing. That gives us the standard error of the difference that we use in the z-score for the two groups case. Now, let's go ahead and calculate with some numbers that we pull out of thin air. So let's say that we are looking for standard error of the difference, where let's say that population 1, let's talk about gummy bears that people eat in a day. So let's say that the variance is, let's say 37, it's a good number, and that n was 52. We're adding, let's say variance of the second one was 13, and let's say 52 again. So let's go through and calculate this. So we're going to have 37 divided by 52 is equal to 0.71. None of the numbers are high enough to round up, so we'll truncate it there, plus we're going to have 13 divided by 52 is equal to 0.25. So we're going to have the square root of 0.71 plus 0.25, which gives us, again, if we'll just put this in parentheses to compact this a little bit, but plus 0.71 is equal to 0.96. So we have the square root of 0.96. And if we wanted to take that, which would give us 0.98 with rounding. So that gives us this number as our standard error of the difference for this made-up set of numbers. Now, if we head on to a new sheet, we can go ahead and see that if we were to plug this into our z-score for groups formula, for the two groups formula, we are going to have x bar 1? Well, if we said variance was 35, let's say mean was 100. Minus, let's say this group 890. We're going to subtract from that the means of the populations that these samples were taken from. Let's say mu1 is 135 and mu2 was 87. And all of this is over that 0.98 that we just calculated. And we'll go ahead, pull that off. And so that's going to give us 10 minus, let's see. My head does not feel up to that task today. 5 minus 87 is equal to 48 over 0.98. So z is equal to 10 minus 48 divided by 0.98, which is going to give us negative 38 divided by 0.98 divided by 0.98 is equal to negative 38.78, which would be our z-score. Now, this z-score is massive. You would probably not see a z-score this large in any data set that you collected, but given the numbers I selected, this is what we came up with. So hopefully this is helpful for you, and you have a better understanding of how to calculate a z-score for two groups, what the standard error of the difference is, and how we calculate it. So until next time, cheers.